next, I think Monday and Tuesday. And I will send out email about it, but I just wanted to give a shout out to all the students and the others who might be interested in the event. Okay, so give more details via email, just look out for that. Okay, so let's get started with today's seminar. So it's great to have Ziteng Sun. He's a student at Cornell University, and he's a fifth-year PhD student in the Electrical Engineering and Computer Engineering department. He's advised by Jayadev Acharya. I guess some of you may have interacted with him. Okay, and so Ziteng has been doing work in like distributed machine learning and the intersection of ML and information theory. And I guess, yeah, he's going to talk about some of his recent work. So yeah, go ahead.
Yeah, thank you, Aditya, for inviting me and the nice introduction. So I'm Ziteng Sun from Cornell, and today I'm going to talk about distributed inference under local information constraints. Yeah, feel free to interrupt me if there's any questions. Yeah. Here is an outline of the talk. So we will first introduce like distributed statistical inference. What types of problems do we consider? And what do we mean by information constraints? And what are the challenges we face here? And then we will focus on the problem of discrete distribution estimation under privacy constraints. We will introduce two algorithms, hard-mode response and the one-bit hard-mode response. We will also study the role of interactivity in this problem. And then we will conclude with some other interesting directions. Okay, so in the era of big data, we are collecting data from all types of devices, including like smartphones, laptops, or even cars. Assuming there is an underlying distribution that generates the data, the goal of the central server is to estimate some property about the distribution to make smarter decisions or to provide better service. However, due to various constraints, the access to this data might be limited. For example, you may not be able to transmit enough data due to low battery or bad connection, or the data may contain sensitive information resulting in privacy constraints, or there might be noise in the data. All of this results in that you can only observe some constrained observations. In this talk, we will study how these constraints affect the performance of the system. Okay, so let's first formally define statistical inference. There is a known alphabet, X, and there is a collection of distributions over the alphabet, denoted by P. And there is an unknown distribution over X. And we assume there are n users, and each of them observe one independent sample from the distribution. And our goal is to estimate some property about the underlying distribution. The goal is to design an algorithm which looks at the samples and estimates the property. And the metric is the loss is measured in some loss function. And we want to characterize the sample complexity, which is defined to be the least number of samples required, such that there exists an algorithm such that for all distributions in the distribution class, the expected loss measured in the loss function that we will define later is bounded by alpha for any distribution in the class. Is the framework clear?
What kinds of mu's will you be thinking about?
Yeah, that's a great question. Like that comes exactly in the next slide. Yeah, great. There are many. It covers a broad family of questions. For example, first is distribution learning. We want to learn the distribution itself, and here the property is just the distribution itself. And for example, stochastic optimization, like there is a parameter space and a loss function, and the property is just like what parameter in the parameter space minimizes the expected loss. And there's like more classic property estimation about the distributions. For example, the property can be channel entropy, support size, or if the data is a graphic data, like connectivity in a graph, like all kinds of these properties. Or it can be distribution testing, like there exists a Q, which is a reference distribution, and the property is just like whether the distribution is equal to Q or not. Okay, so like there are many other problems that can be formed in this framework. And in this talk, we will mostly focus on the first. Any questions now? Great. Okay, we'll continue. So then what do we mean by local information constraints? So because we are considering a distributed framework, so in this case, like the server cannot observe the samples directly. Instead, each user must send their sample, xi, through a channel denoted by wi, and generates a message yi to the server. Okay, and by channel, we mean a probabilistic mapping, such that for all x in the input domain and y in the output domain, wi of y given x is denoted as the probability of yi equals to y, given that the input is x. Okay, so by information constraints, we mean that what kind of channels can we choose? So the information constraints are like imposed in the form of a set of channels that is allowed for the user to use. Let me give some examples. For example, communication constraints, where only L bits are allowed to transmit from each user. Here, the class of channels is just like the channels that output an alphabet of size at most 2 to the L. And for example, privacy constraints, we only allow like WIs that are epsilon locally differentially private. Like a channel is said to be epsilon local differentially private, or LDP, if for any y in the output domain and any distinct pairs x and x prime in the input domain, the ratio between the probability of outputting y given x and the probability of outputting y given x prime is bounded by e to the epsilon. You can see the smaller epsilon is, like the smaller the ratio has to be, and the more privacy we have. Because like you will obtain like less information from the output y about the input x. Let's take the extreme. If like epsilon is 0, then the ratio is 1 for every y and x. So in other words, like the output doesn't depend on the input at all. So we gain 0 information about the input. And the other extreme, epsilon is infinity, like this, we don't have any constraint. So we have no privacy. Is this clear?
Sorry, so do you mean like x and x prime and x that are close or something like that? Or is because it's a finite domain, so you want it for any pair?
Yeah, that's a great question. So like there are two different notions of differential privacy. Like the first is like central differential privacy, where you can see all the data. And your requirement is that like if you change one data point in the domain, in your data set, then your output cannot change by too much. The ratio must be bounded. But here we are talking about the local version of the differential privacy, where
I see.
There is the threat model is a bit different because we are in the distributed setting. We assume the server might be like malicious. So we don't want the server to see the real data. That's a concern. So yeah, in other words, it's like central privacy with only one data point.
I see. Yeah, thanks.
Any other questions?
So should we be thinking of this WI as something that acts on the information, or that's like your transmitter or something like that?
Yes, exactly. Like channel, yeah. And we can also like other constraints can also be framed in this form. For example, linear measurements, like y is a linear transform of x, or noisy measurements, y is like x plus some noise. Like we will focus on communication and privacy, but many of the problems can be tested in this framework. Any questions here? Great.
I had one question. Is RAPO, so I know about an algorithm called RAPO, which was developed by Google. It also deals with similar kind of situation, isn't it?
Exactly. It will come later, literally. Yeah. We will see. We'll see it in probably 10 slides. Yeah. Any other questions? Okay, great. Okay, so So each user has the channel, and then like since we have n users, we need a communication protocol. Like, i.e., like each user needs to select their channel, and then they pass their sample through the channel to generate messages. And how these channels are selected and how the messages are transmitted to the server, like this forms a communication protocol. Okay. There are many aspects of the communication protocol that we can consider. The first is symmetry, i.e., whether each user uses the same channel or not. In practice, symmetric channels are easier to implement. For example, for cheap sensors, you can use the same hardware to implement symmetric sensing schemes. And we will also study, like, and for example, like shared randomness, private coin protocols. What do we mean by that? It's like if WIs are chosen independently or prefixed, then it's like, then it's called the private coin protocol. And for a public coin protocol, we assume there is shared randomness in the system, i.e. there is a U, which is uniform random bits available to all players and the server. And then the WIs are chosen after seeing the realization of U. So U, although the U doesn't carry information itself, but it can somehow coordinate between the channels, so that, and so that it may, there may gain some we may gain some benefit from that. And also, like similarly, like public coin protocols are more harder to implement because you need extra modules. Good. So like then like in this talk, we will study like whether these extra modules of the system will lead to performance improvement in the system. Any questions here? Great. So even more, the communication protocol can be interactive, which means the following. The first user selects its channel first, and then generates its message, which will be sent to the server and all other users. The second user will select the channel based on the message received from the first user, and they will also send the message to the server and all subsequent users. The process goes on, and each user can select their channel based on previous users' messages and send their message to subsequent users. Clearly, this extra sophistication will introduce more challenges in the system design and more communication overhead. And also it will like result in a delay in the communication system because of this interactive structure. But arguably, like interactive schemes are more powerful because it's a strict superset of non-interactive schemes. But is it worth the cost? Whether interactivity leads to better performance is also an interesting direction to explore. Yep. Any questions up to this part? Great. Okay. So it's a very interdisciplinary field, and it requires tools from statistics, machine learning, information theory, and algorithm design. So it's quite exciting to work in this area. And in this talk, we will focus on discrete distribution learning and the privacy constraints. Okay, so we all use emojis to chat now. And suppose the service provider wants to learn how frequently is a certain emoji used, or what are the most popular emojis from users' data. However, emojis are quite informative, which may contain sensitive information from the users. So we need to take users' privacy into consideration when designing these algorithms. So this problem can be modeled as the following discrete distribution learning problem under LDP constraints. In this case, the alphabet is just of size k, and without loss of generality, we assume the data is categorical. So we can assume the data domain is just from 0 to k-1. And we consider all possible, so we consider distribution from all possible distributions supported on the alphabet of size k. And similarly, like there are n independent samples generated from the underlying distribution. And each user must transmit their channel through an LDP channel, which maps their sample into another domain, denoted by Y. And our goal, the server wants to design an estimator p hat, which sees the messages and returns an estimate in the simplex. The loss in this case we consider is just the total variation distance between the estimate and the underlying distribution, which is also equal to the half of the L1 norm between of the difference between the two. And the sample complexity, similarly, is the least number of samples required, such that there exists a sequence of epsilon LDP channels and an estimator, such that for all distribution in the simplex, the expected total variation distance is bounded by alpha. The randomness comes from the randomness of the samples and also possibly the randomness of the channels. It's a definition clear. We will focus on this problem.
As like n is the number of users, a large number of users. K is supposed to be smaller than n, presumably, right?
Yes, that's a good question. Like K is, imagine K is a number of all possible emojis in the example that we have, and n is the number of users. Yes. Any other questions? Great. Okay. So without any constraints, if we don't require the channel to be epsilon LDP, the sample complexity is known to be K over alpha square, linear with the alphabet size. And then, which is can be achieved by the simple empirical estimator. The estimator just returns the empirical frequencies of each of the elements. Okay. So what can we do in the LDP case? Clearly, this estimator is not LDP because you can think of each of the channels which just gives you the original matrix, original sample. In this talk, we will focus on the high privacy regime when epsilon is of order 1, or you can think of epsilon as a constant, which is the most interesting regime in practice because that's where it gives you a strong privacy guarantee for each of the users. The algorithm we are going to present also works for other parameters ranges of epsilon, but for simplicity, we will focus on the high privacy regime in this talk. Okay, before going to the next, any questions about the formulation? Great. Okay, let's first talk about non-interactive schemes. Okay, probably the most well-known algorithm or scheme is called randomized response to do under LDP constraints, which can be dated back to Warner et al. In 1965. Or Warner, not et al. Okay, in 1965. The output domain is just the same as the input domain. It's also of size K. And the scheme is the following. For all input elements, the user outputs the true input with a slightly higher probability, and all other inputs with a slightly lower probability. The ratio is set to be e to the epsilon to make sure that it satisfies privacy constraints. And we properly normalize the probabilities to make sure that it sums up to 1. Is the scheme clear? Okay, and it has been shown that in the high privacy regime, this scheme requires order k cube over alpha square epsilon square samples, which is a factor of k square divided by epsilon square blow up compared to the non-private case. Recall k is the alphabet size, alpha is the accuracy we want, and epsilon is the privacy parameter. And it can be shown that if you use this scheme, so you must have this amount of samples. Okay, is this the best we can do? then like here comes rapport. There's rapport, which is independently proposed by these guys, Ducci, Jordan, and Wainwright, I believe. And then Erlingson et al., they are at Google. Yeah, that's the famous rapport paper. So the scheme is the following. So the output alphabet is a k-length bit string. And what do? We first do a one-hot encoding of the element. What does it mean? It's like, so there is a k-length bit string, and there is a 1 at the location where the data lies in. And all other places, there are zeros. And to guarantee privacy, we flip each bit with probability 1 over e to the epsilon over 2 plus 1 to get 1. So some of the zeros may become 1s and the 1 may become 0, randomly flipping them. And you can show that this scheme satisfies epsilon LDP. And you can see like the true location, at the true location, there is a slightly higher probability of getting 1 there compared to all other locations. So you can imagine we can recover the original distribution from the message distribution of this bit string. And it can be shown that in the high privacy regime, this scheme results in a sample complexity of k square alpha divided by alpha square epsilon square, which is better than the previous scheme. And you can also show that this is actually tight for all non-interactive schemes.
I had a very quick question. Like your previous scheme, the randomized response was only like log k bits of communication, right? But this seems to be like k bits of.
That's a fabulous question. Like that will come exactly next slide. Yeah, that's the motivation for this work. And this is shown to be optimal for all non-interactive schemes. And the questions up to here. Great. So I was about to ask, like, since we have the optimal samples, like, what are we doing here? Like, but since Aditya like noticed the problem about the scheme, let's just jump to there. Like before that, let's mention like the scheme is not optimal for all ranges of epsilon. There's a scheme called subset selection, which is optimal for all parameter ranges, which is similar to this, but we won't go into the details. Okay, so the problem here is that there are many other resources that we need to consider. If we think of randomized response, sample-wise is terrible. We need k-cube number of samples. The communication-wise is good because there's the output alphabet is of size k, so we only need log k bits to send the sample. And time-wise, there is the scheme is very simple, and there is a linear time decoding algorithm for that. On the other hand, bit flipping or rapport, sample-wise is good, k square, optimal for any non-interactive schemes. But communication-wise, it's bad. We need k bits. And you may argue that you can compress the k bits, but actually we have shown that the bit string has entropy of at least order k. So you cannot compress it losslessly. And time-wise, since each user is sending k bits, and there are n users, so you need time n times k to transmit those bits, to read those bits. So decoding time is at least n times k. And the same holds for subset selection. There seems to be a trade-off, like schemes that transmits more bits seem to perform better than those transmit less. And the question is there a trade-off between the communication complexity and sample complexity? Okay. The answer, so yeah, the answer is no. But I want to mention, like, when we first look at this problem, we thought there will be, but the answer is no. We proposed a scheme called Hartman response, which has optimal sample complexity for all ranges of epsilon. And it has log k bits of communication. It only requires log k bits of communication from each of the users. And there is a linear time decoding algorithm for that. And it is symmetric, each user using the same scheme and private coin, no shared randomness. In other words, we get the best of all the worlds. Before going to the details, any questions about the previous works? Yeah. Great. We will move to the scheme then. Okay. The scheme is called Hadamard response. Before going to the specific protocol, let's talk about a general family of privatization schemes. Okay, we first choose K, which is output alphabet size. And then we choose a positive integer s smaller than K. And for each input x, we pick a subset of the output alphabet, Cx, with size exactly s. Let me give an example. Like, for example, if the output alphabet is of size 10 and s is 3, we just set Cx to be the column indices of these black boxes. Okay, and then if we do this for every input, like if we give every input a row of the matrix, and then we do this for every input, we get the sets. And once we have the sets, the privatization scheme is the following. We output our y if the user sees x, and then the user outputs our y that is in the set Cx with a slightly higher probability. And our y that is not, sorry, this should be y. Okay, our y that is not in the set Cx with a slightly lower probability. And the ratio is e to the epsilon to make sure it's private, and we properly normalize them to make sure it's sum up to 1. Is the scheme clear?
So actually, could you go back the previous slide just for a second?
Yeah.
And so Cx is just some subset of.
Yes, yes. We haven't specified it now, but we will do that later.
Yeah. Okay. That's why it's family. Okay, yeah, sure.
Sorry, yeah. Okay. Okay. Any other questions? Great. To make it clearer, like think of this matrix. Like if we set bk to be small k and s equals to 1, and Cx to be the singleton containing only x, then this is exactly the randomized response scheme that we just described. Okay, great. Then let's go into what an optimal scheme looks like. Then we show that if we select bk, if we can do this, let's assume we can do this. If we can select bk to be between small k and 2 small k, and the size of each Cx to be bk over 2. And we also select Cx's such that for any distinct pairs of inputs, the symmetric difference, which is defined as the elements that is contained in exactly one of the sets. So if it is not in one of the sets, it's not in there. If it is in both sets, it's not in there. They're the sets elements that only contain in one of them. If the sets of the symmetric difference for any Cx and Cx prime is k over 2. So in other words, they agree on exactly k over 2 elements. And then we perform the scheme that we just described. And we can show that this scheme achieves the optimal sample complexity of k squared, alpha squared, epsilon squared. And because bk is of size at most 2 times k, so the communication complexity is at most log k plus 1. Any questions here?
So are these factors 2 and so on important here, or does any error correcting code can you convert it to something like this?
Yes, I think actually that's a good question. Like we haven't explored whether the constant factors matter, but you are right. Like any error correction code should work, but we will see like why Hadamard is might perform better than them, like in terms of time complexity, or others might work as well. I agree, like maybe a random matrix will also work if you design a random matrix and CX is also satisfied this. Yes.
Exactly, yeah.
Yeah. Okay, any questions here? Okay, great. So let's talk about decoding first. Like we have this scheme, and suppose we define PCX to be the probability of the output in set CX, given that the sample is sampled from the distribution P. Then we can derive this linear relationship between PX and PCX. Okay. Once we have this, then like we can use the empirical estimator to obtain estimates for PCXs. And then we just do we just invert the linear transform to get estimates for PXs. However, like one thing to note here is that to do this, we need to compute PCX for each of the subset. And there are k of them. To compute the empirical estimator, we need to go through elements, like if we use a naive implementation, which takes time order k for each subset, and there are k subsets. So time-wise, we still need order n times k time, which is still bad based on what we discussed before. Okay, so now there are two problems. Like as Aditya like noticed, like we haven't specified CXs now, and the decoding time is still bad. Okay, so can we resolve this? Or how can we resolve this? So like as a spoiler, like the scheme is called like Hadamard response. So we will resolve this by using Hadamard matrices. Hadamard matrices is a family of matrices which of size powers of 2. Family of square matrices of size power of 2, like recursively defined in this way. And it has the following nice properties. The number of plus ones in each row, except the first row, is m over 2. And any two rows agree on exactly half of the locations. Okay, these seem like the properties we want. And if we choose the set as the following, we choose bk to be the smallest power of 2, bigger than small k. And then we choose s to be big K divided by 2. And we choose CXs in the following way. Suppose small k is 6, then big K is 8. This is what the Hadamard matrix of size 8 looks like. We remove the first row because it's all ones. We don't want that. And then we associate each input with a row of the matrix, and each output with a column of the matrix. Then our set, like for each input, is just the column indices of the row that we associate with that element. And you can see that by the properties of the Hadamard matrices, like these sets will satisfy the properties we want. And if we, any questions up to now? So now we have described how the sets can be selected. And as Dieter mentioned, like probably you can just generate a random matrix, and those factors may not be exactly M over 2. Those should also work. And even a random matrix like will work with high probability. Then like I would say like one advantage of Harman response is the following. There is a fast implementation of the decoding algorithm. So what do we mean by that? If we first use the empirical estimator to estimate the output frequencies of the output alphabet, and then we can show that the estimator we just described can be obtained by a scaled version of the Harman transform of the frequency of the output alphabet. Then, because fast Harman transform, there's a fast implementation, like which can be performed in order k log k. So the overall time complexity is of order n plus k, which is almost linear in the domain size. Okay, any questions regarding this part?
So this is very simple, right? So do people use this? Have you guys?
Yes, I think, yeah. Think yeah, Apple privacy report, like I believe they are using some like Harman response, Harman transform of some sort to implement this.
Wow.
And it's I think, I mean, in industry or practice, I think there are people using this, and like in like the academic community, like the response has been, Harman response has been used for like many other problems as well. Yes. Yeah. I would say it's a very natural thing to think about, like not natural, I mean, if you are familiar with coding, like those things, like and I would say probably it's optimal for, I don't know, that's my conjecture, it's probably optimal for any categorical inference problems. I don't know. Yeah. You can see the idea is just to make the Hamming distance or the distance of the code large. And the Harman is just for fast implementation of the decoding things.
Right.
Yeah. Okay, great. Now we have this. If there's no questions, I will go to the next part. Great. So we have obtained the best of all the worlds, but now the next question is the communication complexity optimal? That's the, like log k is pretty good, but can we even do better than that? Okay, the next part of the talk, communication complexity for LDP distribution learning. Okay, so one part of the problem is known before. If we allow for shared randomness, then this work by Basley and Smith in 2015, they show that in the high privacy regime, any locally private algorithm A, if you can use shared randomness, can be transformed into another locally private scheme, A prime, which only requires 1 bit of communication from each user. And the scheme is private, and the sample complexity is at most twice of the original scheme. With this being said, like you can transmit any of the aforementioned schemes to a 1-bit scheme if you allow for shared randomness, which is good. But as we mentioned, shared randomness might be like it's introduced extra sophistication in the system design of the communication protocol. So a natural question to ask is shared randomness necessary to reduce communication from users? Okay. So the first answer is, if we are focused on symmetric schemes, the answer is no. Or yes, it's necessary. Or no, we cannot reduce the communication. Without shared randomness, any optimal symmetric schemes for distribution learning requires at least log k bits of communication, which is easier to interpret because if every user uses the same channel, then the output distribution of the messages can be viewed as a linear transform of the input distribution. And for that to work, like the channel must be at least of rank k for it to be invertible. Else, like you can find two distributions that result in the same message distribution, which you cannot distinguish them apart. So the idea is simple for proving this. Then what about we are allowed to use asymmetric schemes? Then the answer, surprisingly, is yes. In this work, we show that there exists a private coin scheme, which is asymmetric, and it only requires 1 bit of communication from each user. And it can achieve the optimal performance for distribution learning.
Hey, so I have a quick question. So asymmetric scheme means that like every user still gets an X that is according to the distribution, right? So it's still get a sample. It's just that they choose to use a different code or something like that. So,
yes, exactly.
Oh, okay.
Yes. Okay.
And the server is aware of all of their, like each of their schemes.
Yes, the user, the server knows all the schemes. Yes, great. So, what the scheme then like? What does the scheme look like? It's actually called like 1-bit Hartman response. Sorry. So, which is of course like also related to Hartman matrices. Recall the Hartman matrix and the sets we have defined according to Hartman matrices. The scheme is actually the following. So we assign each user a row of the matrix. Okay, each user looks at a different row of the matrix. And user I is assigned row J if J and I are the same modulo K. In other words, the first user is assigned the first row, the second user is assigned the second row, and the kth user is assigned the kth row. And then for the k plus 1th user, they go back to the first row. So we assign this like iteratively. And then you can see that each row has about n divided by k users assigned to it. This should be bk. Okay. And then the scheme is the following. Suppose user I is assigned to row J. Then the user I just send a randomized version of the indicator function of whether the sample they observe is in the set Cj or not. In other words, if xi is in the set Cj, then the user sends 1 with a slightly higher probability. And if it's not in Cj, it sends 1 with slightly lower probability. And the ratio is e to the epsilon to make sure it's private. Okay, now each user only sends 1 bit, and you can see that like it can be shown that like this scheme has the similar performance as a Hardeman response, and it can also achieve the optimal sample capacity of k² divided by alpha² epsilon².
So the number of the n now increases by what factor?
It's still k² over alpha² epsilon². Still k over epsilon². Sorry, like the sample capacity is here.
Okay. Yeah, I was just curious. I mean, there's no like log k increase, right? So there's just constant factor increase or something.
You mean compared to Hardeman response?
Yes.
At most constant factor, yeah.
Okay.
Actually, in experiments, we observe that like 1-bit Hardeman response even outperform Hardeman response.
Oh,
So
nice.
it's an interesting phenomenon to point out. Yeah. Yeah. In many cases. Okay, so any questions regarding this? Good. So the mission, like for symmetric, these four are all symmetric schemes, and we show that like Hardeman response achieves the best sample complexity, the best communication complexity, and time-wise, like linear up to log factors is the best we can hope for, because you need to read the samples at least, and output the distribution. And for asymmetric channels, we describe 1-bit Hardeman response, order k² over alpha² epsilon² samples optimal, and only 1 bit of communication. And still, we haven't covered this, but similar to the Hardeman response, there is an order linear time decoding algorithm. Is any questions here? Great. One extra thing I want to mention here, because of some recent confusion, like in the literature, is like to sample an element from Hardeman matrix, you only need log k time. So by some bit operations. So from the user side, the time capacity is log k. Like each user can also perform the scheme very efficiently. Yeah. Okay. Then since I still have time, let's go into the next question. Like that's interactivity help. Okay, that's the question. Okay. So previous work, like Duji et al., they showed that for non-interactive schemes, the sample complexity is k² over alpha² epsilon². But notice that extra care needed for proving lower bounds for interactive schemes. Okay, this also holds, like, yeah. And in this paper, we show that actually interactivity doesn't help. They show that the sample complexity for distribution learning under LDP constraints for interactive schemes is also k² over alpha² epsilon². I want to point out, like the most interesting thing is that we developed a technique which can be used to derive lower bounds for other constraint inference problems, not only for LDP. But in this talk, we focus on LDP, and this is the result. And it can also be applied for other constraints, for example, communication constraints, or other like inference problems, for example, testing. And yeah, there are also some ongoing work on like optimization, those things.
So this is, yeah, also probably something that maybe students and others will be wondering. But so the notion of LDP when it comes to interactive schemes, so can you say a little bit about that?
That's good question. Like LDP is like, okay, I think, let me go back to this slide. Yeah, sorry, I should have prepared that.
Yeah, even intuitive is fine actually if you don't have.
Yeah, it's just, I think it's good to look at here. So, so here's what like interactive scheme looks like. So for LDP scheme, interactive LDP scheme, each of these channels must be LDP. So in other words, like each yi should not reveal too much information about xi.
I see.
And then,
so the fact that it's interacting doesn't matter. It's just like you assume that wi is produced something.
yeah,
Is that
wi is selected based on the previous messages. And then like, and the message is still generated from like xi through wi. Yes, is this clear? And another question is like, this is sequentially interactive protocol, and there are more general, broad, another notion of interactive protocol called the blackboard communication model, where each user can participate. It allows for multi rounds of communication, things like that. We are trying to generate our work to Blackboard, and I think it's promising. But the LDP notion is less clear there because you allow for multiple rounds and multiple messages. But there are also works on that. But I think for LDP, sequentially interactive is the most natural notion. Is that clear?
Yeah,
so,
that's good. Thanks.
Yeah. Okay, let's see. Okay, so this, yes. So the math will be a bit scary. To now, I don't think I have enough time for that, but I just want to mention like the result, and I want to mention like here's a summary, like epsilon LDP k-array distribution. We show that like epsilon LDP k-array distribution learning, the sample complexity, it's k² over alpha square epsilon square. And Hartman response, a symmetric scheme, private coin, requires log k bits of communication. And we also propose like 1 bit Hartman response, asymmetric, private coin, but 1 bit of communication. And then we also show that interactivity doesn't help. We want to conclude with some exciting directions like in this domain. So for example, like there are many other interesting directions. Like for example, many real world applications are more structured than categorical data. Like Discrete basically assumes it's categorical. And for example, like there are high dimensional distributions, sparse distribution. For example, like if, for example, emojis, like many of the emojis are not used at all. So the distribution is sparse. In another work, we show that like if the distribution is as sparse, like supported on a smaller domain of S, like basically you have S squared divided by alpha square epsilon square with some extra log factor on K. And communication constraints, like a big chunk of the work in the literature is on communication constraints. Each user has a bandwidth limit. And memory, like data comes in an online fashion, but you don't have enough memory to store all the data to perform an like offline algorithm. And randomness, like beyond just the private coin randomness and public coin randomness, what if you have a limited amount of randomness? Like or public randomness means like you have infinite amount of randomness. What if you have only a limited amount of randomness in the system? And robustness, like it's also a health area. Like what if instead of getting clean IID samples, like there is an adversary which can perform data poisoning attack? And there are many exciting questions here, and I've studied in some of the areas, and I'm excited to see more works in here. Yeah, and thank you. Questions would be welcome.
Yeah, thanks a lot. And Yeah, I guess clapping is the hardest part here. So I think some people figure out the way. This may not. Yeah. So yeah, so these are like, I think, very good questions. Can you actually go back to the previous slide? Then maybe students have. Oh no, like the other. Yeah. So students, if you have questions, you can ask here. Like I had a question about this like structured distributions point
Yes.
that you were asking, that you were mentioning. Like so you mentioned the sparse distributions, right? Like so in these kinds of cases, uh, like can you get some kind of output sensitive kind of algorithms? Like what I mean by that is that suppose there was some distribution over your emojis, and of course you don't know it, but maybe it has some lowish entropy distribution. Can you have like a coding scheme that's doesn't know that, but somehow the communication or the sample complexity ends up depending on that parameter?
That's a great question. Yes. In our work, we actually show that. For example, let's consider just the L0 sparse notion, like i.e. there are only at most S elements that have positive probabilities. In our work, we show that if you don't know S, you use hardware response, like you get the same sample complexity, not the same complexity, you get the sample complexity of S squared. S is the Spartan notion, like times log K. Divided by alpha square epsilon square, which we don't know whether it's tight, but with this you basically replace K with S up to log factors.
Right.
But on the other hand, if you know S, and you can do another algorithm called sparse projection onto the simplex, and what you get is S squared log K over S. If you don't know S, you get log.
What? Log square.
It's log K. It's log K, the log factor.
Oh, now it's like log of K over S. You're saying this
Yes.
is like some compressed sensing type thing on top.
Yes, yes, exactly. Okay. And this is tight.
Okay, I see.
So I don't know whether you can get log K over S without knowing S, but I don't know, but you can get log K without knowing S. And there's another paper which is not in this information constraint framework. It's just in the like where you can observe the samples like without any constraint, that framework. There, the sample complexity is K over epsilon square, alpha square, if you recall, like K over alpha square. And they show that you can without knowing any sparsity parameter, actually the sample complexity is the half norm of P divided by alpha square. The half norm square of P.
So it, I guess by half norm you just mean take everything like just LP norm, but with P equals half kind of thing, right?
Yes.
Okay.
Yes, half norm. Yes. Sorry, it's not a norm. It's I shouldn't say that it's norm. It's like that yes. And then you can actually you don't need to know the half norm, but you can get half norm. That's like, I believe the name of the paper is like learning distribution with infinite support. Something like that. Yeah. So there are some works there. Yeah, it's a very good direction, I think. Yeah.
Yeah, that's cool. Anybody else have questions? Okay, so if not, let's thank Ziteng. Thanks for coming, doing this, and hope to like see you in person sometime. So yeah,
hopefully.
if you go to ITA, so that's a good place to see.
ITA, is it happening this year?
No, not this year.
Okay. It's not okay. Yeah,
cool,
but I really like ITA. Yeah.
Okay. Yeah, thanks. See you.
Okay.
And thanks everyone for coming, and watch out for the announcement about this other event that I was saying next week. So see you.
Okay.
Yeah.
Bye. Thanks a lot
Bye.
for inviting me. Yeah.